Yeah, so the next speaker we have is from University of Toronto. It's Dr. Amar Vutha. He did his undergraduate from IIT Kanpur. Then he did his PhD from Yale University, America. Then he did his postdoc from York University before joining this University of Toronto. So it's a different kind of experiment he's doing. He's trying to measure CPU violations in atomic and molecular systems. And he was the first person who measured EDM, electric dipole moment of thorium oxide molecules. That's due to the CPU violation effects. And I hope he will be talking about those kind of physics here. So with this, may I request Amar to now proceed with your presentation?
Okay, thank you very much. I hope you can all hear me. Thank you to the organizers for, first of all, asking me to give these lectures, and secondly, letting me do these remotely. I realize that it's an extra burden on those of you, and I too would have preferred to have interacted with all of you in 3 dimensions rather than 2, but due to constraints of travel, etc., I couldn't leave, but I'm happy to do this, and I hope this will be fun. So I've been asked to give 3 lectures on roughly this topic of using atoms and molecules to search for new physics that's beyond the standard model. That's what the BSM stands for. And I decided to sort of pitch these at the level of someone who's a beginning master's student or a senior undergraduate. And so I hope that's okay with those of you who are new to the field, but for those of you who are experts in the field and already know most of this, some of this may be boring, and so I apologize in advance. But hopefully you can at least ask me questions that make me sweat a little bit, and we can have some fun that way. I also wanted to emphasize that I at least have been thinking of these as not a seminar talk, not a colloquium talk, but really as lectures, which means these are aimed at the students among the audience. And it also means that to get the most out of this, and for me to get the most out of this experience, I think it's necessary that we have lots of questions. And so please do ask questions at any point. If you want to interrupt me in the middle of these lectures, please absolutely feel free to do so. That's the one thing that I regret not being able to do in 3 dimensions, is looking around and seeing if people have any questions. And so I'll have to rely on you to be please asking questions, be bold, be as bold and as loud and as interruptive as you like. The material I'm going to talk about in these lectures will be broadly covered in these 2 reference articles, this one and this one. Both of these are fairly recent, from about 5 years ago, and so they summarize the state of the field as it is now. I think it's fair to say that with 1 or 2 notable exceptions, there's not really been so much happening in the field of precision measurements in the last 4 years that we've had to write new reviews. Unfortunate, but true. In other words, no one's found any evidence of beyond standard model physics. That's the punchline. But at least the quest is ongoing. And so these 2 articles will hopefully give you a good sense of what's going on. So even if you get absolutely nothing from my lectures, I will at least leave you with these 2 references so that you can follow up on them. But please also feel free to follow up on them between the first and the second, or the second and the third lectures, and bring questions from them if that's what you would like to do. So let me start by asking, are there any questions so far? If not, then I have a question for you. This was supposed to be a lecture on beyond standard model physics. And I started thinking and wondering, what the heck is beyond standard model physics anyway? Do you have any thoughts? Do you have any personal preference for what you would like to consider as beyond standard model physics? Anybody in the audience? You could probably just shout it out. The mic will probably pick it up.
Amar, somebody
Yeah.
is saying supersymmetric models.
Supersymmetric models. Okay, great. Anything else?
Dark matter. Yeah, dark
Dark
matter.
matter. Dark matter. Great. Awesome. Anything more?
Graviton.
Gravitons. Okay. All right. All of these things are correct. But arguably, because the standard model is a theory of electromagnetism, weak forces and strong forces, and um, very obviously does not include gravity, you could technically imagine that if an apple were dropping on Newton's head, that itself is a gravitational phenomenon. And so technically that's outside the standard model. So whoever said graviton, yes, you're on the right track. Anything involving gravity, especially quantum gravity, is well outside the standard model. But that's not what we're going to be focusing on, especially when I say beyond standard model. That's not really what I mean. What I mean is more along the lines of the other two answers. People who said things like dark matter or supersymmetric models or any of that stuff. Okay, so we're not going to talk about gravity. There will be other lectures in this series, and I'm sure there will be very exciting speakers who are going to talk about gravity, gravitational waves, other kinds of fun stuff you can do with gravity. But at least in these lectures, I'm not going to talk about anything to do with gravity. Instead, let's talk about this. So this is the latest and best, most recent results on our understanding of the universe. Depending on where you draw the dawn of human civilization or human endeavors to discover physics, you could argue that the very first person who threw a rock at another person already had a pretty good grasp of classical mechanics. So let's say that was about 100,000 years ago. So in about 100,000 years, plus 2,000 years of the modern era of looking and trying to understand our universe, this picture summarizes the sum total of our understanding of the universe. And it's both amazing and depressing at the same time. It's amazing because we at least know this much. And it's important to appreciate that when we talk about this, we're talking about the entirety of the universe, right? And not just the local vicinity of Bangalore or the Earth or the solar system or anything of that sort. We're talking about the entirety of the universe as far as we can see with telescopes, as far as we can see, all the way back to the remnants of the Big Bang in the form of the cosmic microwave background. So this includes everything that we can possibly see in the universe. And this entirety of the universe consists of just this small sliver of stuff. These are the things that are in stars and planets at ICTS around you, right? The tables you're sitting on, the people you like, people you don't like. So all of that is in here. The rest of this, the vast majority of the universe, as far as we know, in our current state of understanding, is stuff that we just can't see. It's completely invisible stuff. Within that, of course, there is a gradation. About that much, give or take, is a different kind of stuff which seems to behave like matter. And that is a gravitational remark. In other words, it behaves like matter in the sense that it gravitationally behaves like matter. But it does not behave like matter in the sense of any of the other matter that we know about. As far as we know, this other stuff that we call dark matter has really no interactions with electromagnetism. That's the reason it's dark, because if it could interact with light, it would, and we'd be able to see it. We'd be able to see its shadows. We'll be able to interact with it through light in some form or the other. And so really, as someone explained to me once, dark matter is not a great name for it. The better name for it is it's invisible matter, right? It's matter that doesn't interact with light. in any form that we know about. And so the only information we have about dark matter is through gravity. And gravity is such a weak force on the scale of things happening on Earth in labs that the best way we have for inferring the existence of dark matter, studying its properties, knowing that it even exists, is entirely through astrophysical observations. Okay, so all of this entire picture, a lot of this picture basically is due to astrophysical observations. The rest of this invisible stuff is even crazier in the sense that it behaves like a strange form of energy in its gravitational properties. It does not even gravitate like matter, it gravitates like energy densities. And it seems to fill all space. It seems to be uniform in all of space. So it has lots of annoying properties that in some sense we thought we had given up with the fall of the ether in the 19th century. And so that's the summary of a knowledge of the universe. So knowledge about dark energy, again, comes from astrophysics. Knowledge about dark matter also comes from astrophysics. Now, I got into this field of physics because as a high school student, I really enjoyed astronomy. And so I have great respect and regard for astrophysics. But at least to me as an experimentalist, astrophysics is deeply unsatisfying. Because astrophysics to me is sort of like going to the zoo. Okay, you go to the zoo. If you're lucky, you get to see some animals doing something interesting. But most of the time, at least in my experience, you go to zoos and the animals are sleeping contentedly under trees, not doing very much, just sort of hanging around. But if you get lucky, you go at feeding time when some exciting thing happens. But for the rest of the time, you have to be sort of content with looking. Whereas experimental physics has more of the flavor of breaking into the enclosure of the tigers, poking them in the nose, and then seeing if they bite you back. So that's experimental physics, and that's the sort of more fun thing for me anyway. And so as an experimentalist, this state of affairs is deeply unsatisfying because we so far have no experimental ways, at least in labs, in the sense of actually being able to poke them to study either dark energy or dark matter. The only things we've been able to test, so far at least, involve this stuff. And this stuff is the content of what we call the standard model. So the entirety of the standard model, everything you've heard about, quarks, leptons, Higgs bosons, gauge bosons, all of that stuff is this tiny, tiny, tiny sliver of the universe. Okay. And so that's the amazing thing. And that's also the depressing thing, is that we only know this little bit, but we do know this little bit really well. Right. This is basically what many physicists have spent many years studying. And so let's dig into how people know about the standard model a little bit. And so to a pretty good approximation, this is how we know about the standard model. And so there's been one extremely successful experimental algorithm or experimental method for finding physics and understanding the properties of the standard model. And this extremely successful procedure, extremely successful algorithm, has worked really well for close to 75 years. Okay, I roughly draw the beginning of the era of particle colliders from around the 1940s with Cockcroft-Walton accelerators and generators, all the way to the latest fanciest machine, which is the Large Hadron Collider. And here's a view of the Large Hadron Collider. I'm sure many of you have seen many other views of this machine. And this algorithm or this procedure has worked extremely well. And the algorithm goes like this. You take a thing, take another thing, speed them up, smash them really hard, and all kinds of interesting things come flying out. Okay, so that's the algorithm. It seems very simple, but it's been extremely successful as a way of helping us understand how to do interesting physics and find new particles, find new forces, all that fun stuff. Okay. And so obviously all of you have heard about and know about discoveries like the Higgs boson, and we wouldn't have had those without colliders. If we had not had colliders, I think we would have possibly found other ways to maybe suspect or infer properties of the Higgs field, but there's nothing quite like seeing Higgs bosons come flying out from collisions for you to be certain that the standard model works well. Okay, any questions so far?
Yeah. Yes, Amar, yeah, wait.
Yeah.
Hello. Yeah. So in the previous slide, you have shown the invisible matter, right? Yeah.
Dark matter, let's call it what everyone calls it. Yeah.
So this is partitioned into dark energy as well as dark matter.
I wouldn't call it invisible matter. I would just say all the rest of the things in the universe other than the things which are part of the standard model.
Okay.
And that's divided into dark matter, which gravitationally behaves like matter in the sense that it makes, very loosely speaking, it makes the universe contract, right? It causes things to, causes other matter to be attracted to itself.
Okay.
And then there's dark energy, which behaves like an energy density with a sort of slightly strange dispersion relation. And so it makes the universe accelerate in its expansion. And that's how we know about dark energy. So what's your question?
So just a slight clarification I need, that considering that both of them are technically invisible, how do we, even based on their effect on our world, on the universe, how do we exactly differentiate between what part of it is energy and what part of it is matter?
That's a fascinating question, and that's a question that you should definitely ask any other people in this school who talk to you about dark energy or dark matter. But that's a question that I think if we get into, we will go very, very far afield. And admittedly, that is definitely beyond standard model, but that'll push us beyond the standard content of whatever it is that I was planning to talk about. Okay, so I will sort of punt that question. I'll just say that again, the way we know about these is because they have different effects on certain aspects of astrophysics. So, for example, with dark matter, what you get is you get gravitational lensing because it behaves gravitationally. And so, if you've got a galaxy and you've got dark matter around it, or dark matter is part of it, then that tends to bend the light from galaxies behind it. Okay, and so that bending of light allows you to infer how much stuff, how much matter there is, how much gravitational matter there is in a galaxy. And then you can look through a telescope, look at that same galaxy and say, hey, wait a second, if I look at the actual light from all the stars and I add up all the matter and all the gas and all the stars, and then all the gas clouds and everything else that I can see, and emits light in some form, infrared, visible, X-rays, whatever, you find that you come up with a deficit. You find that the amount of matter you infer by looking through a telescope is much smaller than the amount of matter that you infer by looking at the gravitational properties of these galaxies. Okay, and so that's how we know about dark matter. There are other clues as well, such as the cosmic microwave background, but at least this is one of the strong pieces of evidence, certainly. Dark energy is a little bit different. And so you probably know about Hubble's law, that if you start off this model of the Big Bang with the right ingredients, it makes the universe expand. But people who started measuring the expansion rate of the universe realized that the universe is not just expanding, it's actually accelerating in its expansion. It's expanding faster than you would expect. And that extra acceleration in its expansion is slightly bizarre. And arguably, in some form or the other, Einstein sort of mathematically kludged his equations of general relativity and put in a term that leads to exactly that sort of thing. So that's called the cosmological constant. And then using observations of galaxies and how far away they're moving away from us, basically the same sort of measurements that Hubble would have done. Again, I'm sort of compressing many decades of serious astrophysical work into 2 lines, but basically people observed that galaxies are speeding up in their expansion. Okay, and this is what leads us to know that the universe is sort of accelerating in its expansion. And the only model we have for explaining that at this point is to postulate that there's a cosmological constant, very much like Einstein put into his equations in the 1920s, and that's what we call dark energy now. Okay, so that's my sort of 2-minute summary, if you like, of these. But like I said, this is a deep and very interesting question in itself, and I encourage you to follow it up. Is that okay?
Go ahead.
Okay, great. Good. Thanks for that question. All right, so let's go back to these. And then, so as I was saying, through colliders in the last 60 to 70 years is how we know all the properties we know about this slice of the universe, which we call the standard model. Now, I will leave you with an even more unsatisfying feature. It's tempting to look at these kinds of graphs, or this particular graph, and say, okay, look, all of this stuff, all of this invisible stuff is, we don't know what it is. It's strange, it's scary, it's exciting, great. But at least this thing, this red slice, the stuff, this must be amazing, right? This is great. We know it really well. We have a complete thing called the standard model. The answer is not quite. And to realize that there's yet one more mystery hiding in this very simple pie chart, we can do an experiment. And we can even do this as an experiment in the room that you're sitting in. And the experiment, which I would like you to think about doing, you don't have to actually do it, but you'll see how it's such a simple experiment. The experiment is that you can reach over to the person sitting next to you or your nearest neighbor, and you can shake their hands. Okay. And you can shake their hands and you don't instantly explode and turn into a shower of photons. Right. And so that very simple experiment already tells you that at least the person sitting next to you is made of the same kind of matter as you are, and not the opposite kind, or not from antimatter. All right. And so we can at least be sure that anyone that you've ever shaken hands with, or anyone that those people have in turn shaken hands with, everything, all of that is made of matter. If you're standing on the Earth, we can again kind of infer from arguments like this that the Earth's made of matter. But you can sort of extend this argument through continuity. All right. In other words, if there's any part of the universe where it's not extremely matter dominated, and let's say, for example, there was some galaxy which was an antimatter galaxy. Well, the space between galaxies is not empty. There's still some gas there. And at least the gas in our part of the galaxy is the regular kind of gas. It's matter gas. In other words, it's helium, it's hydrogen, it's not anti-hydrogen, it's not anti-helium. But if there was some antimatter galaxy, and because we don't see evidence of strong annihilation gamma rays from those galaxies, we can at least infer that within that galaxy, whatever they have is the same kind of thing as their stuff. And so if you postulate that, okay, there's maybe one of the galaxies we see in the sky is an antimatter galaxy. Well, at the boundary between that antimatter galaxy and sort of our matter galaxies, regular kinds of galaxies, from that boundary, where the matter meets the antimatter, we should really be expecting to see extremely clear signatures of annihilation gamma rays. And nobody has ever seen this. Okay, and so that is basically the kind of continuity argument that leads us to believe that the entire universe, as far as we can see, is made of stuff. It's made of matter. And that itself is very surprising, because the standard model, if you believe the math, if you believe the Lagrangians and the Hamiltonians and all the quantum field theory, which the theorists have done, everything about the Lagrangian, the standard model, everything about the properties of everything in the standard model, they treat particles. Let's imagine that you have a proton and antiparticles, antiprotons, okay, or electrons and anti-electrons. The properties, the interactions, everything to do with the cosmological evolution of these things, as if you put in all the physics that we know from the standard model, should have led to equal amounts of electrons and protons as anti-electrons and antiprotons. And so the very fact that we ended up in a universe that seems to be extremely matter dominated is actually also a huge question. It's a very surprising fact. So I would actually claim that we don't even understand this tiny slice. Even this tiny slice is very strange, because even though the properties of things we can produce in colliders and study at colliders and through other kinds of experiments exactly match the standard model in the labs, something between experiments in the labs and the entirety of the universe seems to imply that even the standard model that we know and love is not quite complete. And so we should actually add to this picture a statement that there's stuff which is explained by the standard model, but none of the anti stuff, which is also should be explained by the standard model, is anywhere in the universe. There is no anti stuff anywhere in the universe. Okay, and so in addition to dark energy, dark matter, dark energy, even this very small slice, this 4 to 5% of the universe, there is actually also a mystery hiding in here. And so this, in my humble view, is in one simple diagram, a summary of all the things we don't know about the universe. And to me, these are the most exciting questions in the sort of, I don't really want to call it fundamental physics because it makes it seem more important than other kinds of physics, but in the sort of physics that tells us about how the universe is built up. Okay, so in that sense, fundamental in the sense of building blocks. So in that area of physics, in that area of fundamental physics, these are the three big mysteries. What is dark energy? What is dark matter? And what happened to all of the antimatter that should have been around? Don't get me wrong, I'm happy there's not much antimatter around, because if the universe had just as much matter as antimatter and it filled up the room I'm sitting in, I would not be able to lecture to you this beautiful morning. Or evening, as in your case. And so the fact that we exist is already a fortunate consequence. But nevertheless, we should be curious and we should be wondering why there's no anti stuff. What happened to all the antimatter? Okay, so that's what I really mean now by beyond standard model. When I say that, I mean dark energy, dark matter, and this question of where's all the anti stuff. Great. Okay. So this is again my as I promised, these lectures would be idiosyncratic. I'll say and do things which may cause some slight offense to some people, and I hope you take it in the right spirit. But this is my summary of where we are in terms of trying to understand the properties of the universe using colliders. So with colliders, we've already exhaustively studied everything we can by smashing stuff together. Okay, and it works really, really, really well. But the clues to what's going on appear to be, at least, outside the reach of these colliders. Right? They're in the dark. They're not in the realm of energies or phenomena which we have been able to study, at least so far, through colliders. I may be proven wrong. Between now and my third lecture, someone might actually announce the discovery of a new physics phenomenon at the Large Hadron Collider, at which point I will say, okay, great, there's no point of me giving these lectures. But at least assuming that an earth-shattering event of that sort doesn't quite happen, the point is that at least with colliders, we have no way, or so far at least, we have not found any evidence of physics beyond the standard model. Okay, and so that's the argument for why we should probably be looking for the solution to these puzzles in some other way, in some other means, in some other types of experiments. And I'm not at all guaranteeing that the kind of experiments I will talk about are the exact correct experiments. It's entirely possible that those experiments are also barking up the wrong tree. But we have to try in some way to do something that's different from colliders, and that's the spirit of these sorts of experiments. Great. Okay, all this is great. This is a great story about how physics is incomplete and how we need to look harder. But why, of all the ways in which you could look for all these things, why should you do this using atoms and molecules? And if I was trying to be sort of completely honest and think about why I'm doing what I'm doing, I would immediately say, wait a second, there are two obvious problems with this whole idea. If someone comes to you on the street and say, hey, look, I'm going to look for beyond standard model physics, and I'm going to look for it using atoms and molecules, you should be surprised and you should be suspicious, and you should basically tell this person that they might be, might be on something, some illegal substances, because here are the two things which are wrong with this idea of looking for new physics using atoms and molecules. We know from chemistry, even, or physics, if you've taken it, the physics of matter, etc. We know that the energy scale of things like atoms and molecules is sort of roughly 1 electron volt. Okay, if you don't buy that story, there's a simple experiment you can do. Pop open your phone or any other device which uses a battery, and look at how much voltage that battery produces. Unless you have a stack of a zillion cells inside your battery, most batteries will produce somewhere between 1 to 10 volts. Okay, and there's a reason for that. The reason for that is those batteries rely on chemistry, but chemistry is just atomic physics. And so those batteries basically rely on the properties of atoms. And it takes on the order of an electron volt to rip electrons, or at least the outermost electrons, out of an atom. And so the same reason that batteries are all sort of 1 volt, 3 volts, 9 volts, etc., is basically a clue to you, if you've never thought about this, that atoms are sort of electron volt scale objects. So why should this electron volt scale object have anything to do with physics that's beyond the standard model? Because the LHC works at tens of tera electron volts. Okay, so let's even call it, it'll be 13 electron volts. So the LHC has 13 orders of magnitude in energy higher reach than the sort of experiments you could possibly do by messing around with atoms and molecules sitting in some small lab. And so despite these 13 orders of magnitude, so why do you think that where the LHC has failed, why do you think you could possibly do better with these ridiculous low energy electron volt scale things? And that is a fair question. That's an important question, and it's important to sort of realize why this is even possible. Okay, so that's a major question. The second thing is, okay, great. Let's say you even convince me somehow that you're going to look for new physics. What's an atom? An atom is basically some charge with some other charges floating around outside it. Okay, and these charges, okay, they go around in some interesting way, quantum mechanics, all that fun stuff. But fundamentally, the forces holding together an atom are all electromagnetic forces. They're, in some sense, they're 19th century physics, they're 18th century physics even, right? It's there's not very much exotic stuff going inside an atom. When you study about the chemistry of atoms or the structure of atoms in undergraduate courses, you don't start talking about top quarks, and you don't start talking about Higgs bosons. Yeah, those things are all there in the substructure of the protons and deep inside the nuclei and so on. But at least for the purposes of chemistry for atomic physics, all that's going on really is electromagnetism. Okay, and so that's some physics that we know really well, that we understand really well. People have been testing it for more than 100 years. Why, oh why, do you think you'll find the clues to completely exotic, crazy things like dark energy, dark matter, the presence or absence of antimatter? Why do you think you'll find any clues to that by looking inside a thing which is held together by electromagnetic forces? Shouldn't you really be building a bigger collider and smashing things even harder and trying to dig out new physics? Okay, so those are my two questions. And I'd like you to think about them, and I'd like to hear if any of you have any thoughts or ideas on why this is even a relevant way of looking for new physics. You're all here. Presumably, you decided to waste some of your time listening to me talk about how to look for new physics with atoms and molecules. So at some level, you at least are probably not a complete skeptic about this field of study. So I'd like to hear your thoughts on why do you think this field even works? Why is this even possible?
Just a
It
minute.
seems crazy to me.
So the first uh, proof of quantum electrodynamics was experimentally searched in atoms, right?
Yeah.
So maybe that's why. So it is possible. There's a precedence.
Okay, so let's call that history. And brackets, I'll write things like QED was great. It was amazing. And it was amazing. Let's remind ourselves in 1947. Okay, cool. All right. Any other suggestions?
There is no more suggestions. You may go ahead.
Okay, so I'll just pour some water on this history point, which is that true. We have some historical evidence that, at least in the dawn of quantum electrodynamics, the evidence for basically the clues to this fact that all was not complete in our understanding of electromagnetism or the structure of atoms basically came from measurements on hydrogen atoms. That said, just because it worked once in 1947 doesn't mean we should keep doing it in 2017, right, and beyond. And so this is a slightly iffy thing. But if you stare harder at this, in fact, you're right. There are clues in this very same idea, which led to hydrogen, leading to clues to quantum electrodynamics. Okay, so there is some of that going on. Great. Okay, so let's take the two objections one at a time, and let's sort of break them apart. So the first objection is that we're talking about electron volt scale objects, and I'd like to show you that there's more to this. So one of my favorite textbooks ever is the book on electromagnetism by Purcell. And in that book, Purcell does this really neat thing where he shows that if you have an atom and if you apply an electric field in the lab, well, the atom, what happens to it? The atom gets distorted. Right? The plus charges and the minus charges separate. The atom gets a little dipole moment. And then he sort of argues for how big this dipole moment should be. And I want to repeat this argument because I'm going to use the same argument to give you a sense for why we can use atoms to look beyond the standard model. And so Purcell's argument is, he says, well, look, if the atom deforms, let's say it deforms by an amount that's equal to d, the amount of deformation compared to the size of the atom, because this deformation is due to an electric field, and that electric field is fighting the electric field that's inside an atom, this deformation should be on the order of whatever the lab field is that you apply to the field inside an atom, which is E squared over field. It's E over that. And if you follow this argument, in fact, you end up with the correct expression for the polarizability of atoms. It's you get the right scaling, you get the right dependence on the size of atoms that goes as A naught cubed. You get all that sort of fun stuff. Okay, so this kind of argument is powerful, and so let's apply it to understanding what happens now, not to an atom because of some electric field, but because of some crazy new physics. So let's say you have some new kind of interactions, some crazy forces which are exerted by things which you know nothing about. And what they're doing is they're affecting the properties of the atom. And so let's see how much the properties of these atoms should shift. And so again, my claim is that if these forces exert, or if these new interactions or new particles exert some kind of forces on your atom and change the energy levels. Let's now talk about energy levels instead of deformation. The change or the shift in an energy level of some atom. Okay, this is now a change in energy. And we'll compare it to the sort of EV scale, which is what we've said is sort of the energy scale of the binding of the charges inside an atom to each other. And so how big is delta E compared to an EV due to all this new physics? Well, the claim is that it's going to be on the order of however large this new physics scale is, okay, compared to an EV. In other words, the energy shift of an atom is going to be on the order of sort of an EV times an EV compared to whatever the energy scale is for all this new physics. And so let's say that there's some physics hiding at energies which are just beyond what the LHC saw. Okay, so let's hide this energy scale at, let's say, 10 to the 12 electron volts. All right. Which means that the energy shift you would expect from this kind of argument is that you would expect to see 10 to the minus 12 electron volts, or a pico-electron volt. But let's write this in experimentalist units. An electron volt is 250 terahertz. Okay. And that times 10 to the minus 12 brings us to an energy shift that's on the order of 250 hertz. 250 hertz is a pretty small energy shift for an atom. That's exactly what this 10 to the minus 12 is telling you. It's an extremely small fraction of the energy scale of an atom. But these days, and I would say certainly for at least the last 30 or 40 years, using the techniques of atomic physics, 250 hertz is actually not a hard thing to measure. In fact, 250 hertz is a large thing to measure by modern standards. It's an enormous shift in energy by modern standards. We can measure in the lab energy shifts which are 1,000,000 times smaller than this with a high degree of confidence. Okay, and so that's the answer to this point, which is that yes, it's an EV scale object, but we can now measure energy shifts which are at the level of 10 to the minus 6 hertz. Okay, which should give you a sense for how large an energy reach you can get to based on the simple argument. So if we can go 8 orders of magnitude better than this 250 hertz estimate, that means you can, if the scaling is true, test stuff going on at 10 to the 20 electron volts. Okay, that's an enormously high energy. That's way beyond anything you can measure with the LHC. You might argue and say, okay, wait a second, the scaling is too naive. Maybe this is second order. Maybe this is third order. Maybe this is nth order. Okay, at that point, you stop being able to study 10 to the 20 EV. Maybe you're studying 10 to the 10 EV to second order, etc. But the point remains that even though these effects are small, we can measure things which are even smaller. Okay, so that's really the counter argument, and that's basically what makes this field possible, at least part of this whole enterprise possible. Okay, it's an EV scale object, but we have micro hertz scale, okay, sensitivity, which is approaching 10 to the minus 20 electron volts. Great. The second thing is, these are held together by electromagnetism, which is a super well understood force. So how do we think we can get at any of this interesting new physics? Let's stare at the periodic table. And what I'm going to do is draw some circles around atoms which have been used for these kinds of precision measurements, starting with that, in some form, that, Here we go. You see the pattern. There's that. I'm using that in my lab. People have used that. Definitely that. And then if you include the atoms that are inside molecules, certainly use that. Use those. People have used. Yeah. Okay. So that's a reasonable sort of starting set of circles around the atoms that people have used. You'll see that these atoms are really quite complicated, right? They're not just hydrogen. People have been using atoms like lead, which have 82 electrons, 82 protons, 126 neutrons. And so, yes, atoms are held together by well-understood forces, but there is a point I want to make, which is that atoms and molecules, I'll use atoms, but by extension, molecules as well, these are assemblages of strongly interacting fermions. And it's a very complicated assemblage. It's not as though these are all going around in nice, beautiful circles, right? They're all correlated. You'll hear in many of the forthcoming lectures about the properties of many electron atoms and things. These electrons behave in some horribly complicated way. They're all sort of Pauli excluding each other. They're all pushing and pulling on each other. The nucleus itself, inside it, has some crazy physics going on. And so, in fact, I would say, yes, they're well understood forces, but these are complicated systems. Despite that, there's a reason why this field becomes possible, and it kind of comes down to the following. So let's even stick with electromagnetism and understand why this is possible. So the first thing to realize is the following. Electromagnetism is well understood. But electromagnetism, the laws of electromagnetism, the Lagrangians and the actions of electromagnetism, if you want to be mathematical, have a number of very interesting symmetries. So electromagnetism is parity invariant. It doesn't care which way you define the handedness of a screw. Electromagnetism is also a time reversal invariant. If you make a video of electromagnetic phenomenon and you play that video backwards, you won't be able to distinguish which one was the forward video, which one was the backwards video. If you watch an electron going around in a magnetic field, you can play that video backwards and you would say, well, looks like an electron going around in a magnetic field. Yeah, okay, differently directed magnetic field, but still electron in a magnetic field, okay? It's not like there's friction or any kind of breakdown of time reversal. It's also Lorentz invariant, right? Electromagnetism had contained already in the 19th century the seeds of relativity. And so this is both Lorentz invariant, but it's also space-time translation invariant. And so I'll just write this as Poincare invariant. And so these properties, time reversal symmetry, parity symmetry, and then, of course, it's also charge conjugation invariant. And so that's how you get the C, the P, the T, and then there's another P, which is Poincare invariance. And so electromagnetism is a piece of physics which has lots of symmetries. And even if you look at a lead atom and say, oh, this is some horribly complicated thing, or you look at a thorium oxide molecule and you say, oh, this is some horrible complicated thing involving lots of electrons and nuclei and things flying around, it's not that complicated because underlying all of it are these beautiful symmetries. And these are not just sort of abstract things, they lead to measurable properties. For example, if you write down the generators or the things that actually make these symmetries act upon, let's say, a Hamiltonian. So any of these above symmetries, and we'll call them sigma for symmetry, any of these symmetry operators acting on a Hamiltonian of any atom that you can think about, as long as that Hamiltonian only contains electromagnetic interactions. In fact, you can even lump in strong interactions if you want to be bold. But let's stick with E&M. And so almost all of the physics of a lead atom, for example, involves electron-electron repulsion, Coulomb interactions, electron-proton attraction, Coulomb interactions, electron spin-spin interactions, which are through their dipole moments, through their charges. And so all of this is sort of standard textbook electromagnetism. And so the entirety of this complicated Hamiltonian, whatever it is, if you write down any of these symmetry operators, they commute with these Hamiltonians. Okay. And in quantum mechanics, what that means is you can diagonalize these operators at the same time as you diagonalize your Hamiltonian. But that leads to a very interesting phenomenon. It means the following thing. It means you have names. It means you have labels for your quantum states. And I'm also going to call these labels quantum numbers or good quantum numbers. What do I mean by that? Let's say you have some multi-electron atom and I draw its energy levels. It'll have some complicated pattern. It won't look as beautiful as hydrogen. And you say, wait a second, there's some crazy complicated multi-electron thing. What can I possibly even write down as the labels for these states? What are the conserved quantities? And the answer is these are all the conserved quantities. Poincare invariance always means that you have energy conserved, you have angular momentum conserved, and then you have Lorentz invariance. Okay, so for example, then you can take any of these states and you can always label these states using a bunch of labels. You can label them by their energy. You can label these states by their momentum. Okay, and I'm talking about the total momentum of the entire atom. That'll become relevant in the context of things like atom interferometers. But in addition, you can also label them by their symmetry properties under C, P, and T. And so usually when you talk about atoms, you're only talking about either matter atoms or purely antimatter atoms. So people ignore the C label. But you can label these states by their signature under parity transformations. You can label them and say whether these are positive or negative under parity. You can also label these states by a certain label, which has to do with their time reversal symmetries. Okay. And so even if you know nothing about this multi-electron, many-body, strongly interacting system, even if you cannot solve its dynamics exactly in closed form, you can always guarantee that as long as it's made out of electromagnetism, you can label it with these labels. And these labels are important. It means now that even if you have some very complicated atom and you're trying to study it, if there's anything which breaks any of these invariances, any of these symmetries, then those will show up in the form of atomic and molecular properties. Those will show up in the form of either some energies being slightly different from what they were supposed to be, or it'll become evident in the form of transitions between states, which used to be completely forbidden due to symmetry reasons, becoming slightly allowed. And those are the two main ways in which we can look for breakdown of these symmetries. Because again, if the symmetry leads to energy conservation, momentum conservation, etc., you can look for a small shift or a small breakdown of these things. If these symmetries lead to parity and time reversal symmetry being good symmetries of atoms and molecules, we can look experimentally for breakdown of these things. Okay, and so that's the basic idea again. And so that is why these two are not major problems. In fact, I would almost say these are features, not bugs, if I were to adopt the language of software engineers who you might know. And so the point is, yes, these are EV scale objects, but now, especially with modern techniques of manipulation of atoms, control over their quantum states, all the stuff that was invented possibly for studying many-body physics or building quantum computers or some of that other stuff, we can steal all of those techniques. Okay, and so all those techniques are available for us to measure, control, check the properties of atoms to an extremely good level of control. And that's why, even though these are EV scale objects, we have this advantage, and therefore we can look deeper into the structure of atoms or look higher or look farther in energy scale to find new physics. And the second thing is, yes, these are held together by well-understood forces, but that's entirely the point. Because these are held together by well-understood forces, they have a high degree of symmetry, and therefore any breakdown of these symmetries leads to measurable properties, which we can go and look for. And that's what I'll discuss in the forthcoming lectures. Okay. And so with that, I want to stop, but I'm happy to answer questions for as long as people want to ask them.
Thank you, Amar. There
Thank
is
you.
one.
So the breaking of these symmetries, so you have a atom, let's say, that is made of matter only, but not antimatter.
Yeah.
So I don't get how breaking of this symmetry will lead to some other because you explained that antimatter doesn't, so matter doesn't interact with dark matter.
Yeah.
So how are you saying that these breaking of symmetries lead to some interactions, that is interaction of dark matter, because it is still it's only matter, not antimatter, that is interacting with something that we don't know?
There are two counter things, I'll say. So it's not true that we can only work with atoms. Many people have done sort of decades of very beautiful work to cool and trap and laser cool and study the properties of anti-atoms. So the first remark I'll make is that anti-atoms are actually an experimental reality. Okay, so we can do experiments on anti-hydrogen, and people can do extremely sensitive experiments on anti-hydrogen these days. Not quite anti-helium.
No, Amar, the question is slightly different. What is saying
I understand.
is,
I'm getting there. I'm getting there. Yeah. So the first thing is that it's not that we only have access to atoms. We also have access to anti-atoms. Okay. And therefore, we can do studies of things like breakdown of C symmetry by looking at the properties of atoms compared to anti-atoms. But the second point you had was that, well, so let's say you're talking about regular atoms. You say that you're studying some properties due to breakdown of symmetry, but if matter never interacts with dark matter, then how do you look for it? Your question has the seeds of its own answer. If matter absolutely is completely and utterly forbidden from interacting with dark matter, so let's say there's absolutely no connection between these two sectors. Dark particles, dark forces, they sort of live off in their own universe, and there's absolutely a hard wall due to some new symmetry that we haven't yet discovered in physics that completely prevents any form of interaction between dark matter and matter other than through gravity. Then I would say we're done. If it doesn't interact at all, then yeah, we can't look for it. Okay, at that point, we're stuck with only doing gravitational experiments. So the hope is that there is still some bridge possible. It may be a very, very weak bridge, but if there's any bridge at all possible other than through gravity, then we'd like to look for it. And as far as we know, there's no principle yet discovered. And even if it was, I wouldn't believe you. Even if you did some amazing theory tomorrow and came and told me, yes, I've discovered a new principle of physics that says there can be no interaction between dark matter and matter, I would still say, okay, but let's see what else your theory predicts, and let's go see if that's actually true. That's an experimental question. But the point remains that if for some reason there's absolutely no interaction possible between dark matter and matter, then yeah, then I would say we would never see any direct interactions. Does that answer your question?
Yeah, that answers, but just one point is, if that even that is the case, then breaking of this symmetry will lead us to interactions by which matter is interacting to those interactions, not
Yes.
dark matter, right?
That's fine. Yeah, that's our only signal. That's our antenna. Our antenna is made of matter.
Okay.
Yeah.
Thanks.
I have a couple of questions.
Yeah.
So in your 11th slide, you said that delta E by EV is proportional to EV by E nu. So
Yeah.
how does that, where does that come from? And the second question is, you said that there's a disparity between matter and antimatter in the universe, but all that quantum field theory or standard model predicts is the number of particles minus number of antiparticles. It should be constant, not, they should not be equal, right? Need not be equal.
Okay, all right. So let's take those one at a time. So where did this scaling argument come from? It's a physicist's intuitive argument in the sense that it might be completely wrong, but it feels right. Okay. And so again, the idea is, let's say you have an atom and you have something that's distorting it. So I have a nice, beautiful atom and I have something that's slightly distorting its properties. How much of a distortion do you expect? And I'm trying to quantify the amount of distortion of this atom in terms of the energy shift of some eigenstates of this atom under the influence of this interaction. So you can think of this as basically saying the same thing as first order perturbation theory. The claim is that whatever this new physics is, it leads to an extremely small perturbation, which you can evaluate in the same way as you would do first order perturbation theory. Okay, so this argument here is sort of like a classical version of first order perturbation theory. It basically says if you have some new kind of interaction and it's distorting your atom, how much of a distortion do you expect? Well, the amount of distortion I would expect compared to, the scale of energy in an atom that's already built into it, which is an EV, is on the order of how much this atom's interaction, how much its energy that it has inside is smaller compared to this energy scale of new physics. Okay, so another way to think about this is the inverse of an energy, again with h bar and c being fixed numbers, as you heard about in one of the previous lectures. Inverse of an energy is like a length scale. So this thing on the right-hand side is the same thing as the length scale of new physics divided by the length scale of an atom. Okay, and so this is like saying if there's some physics operating at some crazy small length scale within an atom, how much is it going to shift the energy levels of an atom? And the sort of first order answer, and that's all this is sort of a first order answer, is that the first order, it would distort an atom by roughly the ratio of whatever this new length scale is to the size of an atom. Okay, this is by no means a rigorous argument. Like I said, you could argue, well, maybe the effect is second order. Right, at that point, then what you'd have to do is you'd have to take this whole thing and square it. And then what you would get is you would get an energy shift, which was much smaller than 250 hertz. Okay, and so it just kind of depends on how this new interaction enters into the Hamiltonian that affects an atom. And there are certain effects which are measurable and certain effects which you have to now come up with some arguments to explain why they don't work in first order. Maybe there's some protection against them entering atomic physics to first order. Maybe they only enter to third order or fourth order or whatever. And then, okay, at that point, the measurable effects become smaller. But that's exactly the kind of stuff we're testing.
I see. Thank you.
Your second question was, remind me again.
Yeah, so it was about disparity of matter and antimatter. And
Matter and antimatter. Okay, yeah, right. So your point is that the standard model only talks about what happens to matter and antimatter that already was there in some extent, right? But that's not quite true, because in the standard model, matter and antimatter can convert into each other, right? They interact with each other, but they can also convert into each other in some way. Now, again, the sort of properties of the standard model, like baryon number conservation, which we don't exactly know why, but it seems to be true. But at some level, again, we're talking about new physics that could allow at some crazy energy scales where these symmetries are not broken, processes like these to happen, especially if you're talking about the early universe where the energies were as high as you can possibly imagine. Okay, and so then the point becomes the following. You can always say that, okay, there's something different about the fundamental laws themselves for matter compared to antimatter. And that's why there's no puzzle. And that's why it's not a big mystery, because, yeah, there's something special about matter. But that's, again, slightly unsatisfactory because you sort of postulated a sort of initial condition argument. Right. And again, as far as we know, the initial conditions for the universe was that everything was made of energy. And all the matter and antimatter had to form from that energy. But we still think charge conservation was still active even in the very early universe. And so the point is, if you start with energy and make matter, you have to make an equal amount of antimatter just from charge conservation. And so that's the puzzle. You start with energy, make equal amounts of matter and antimatter, and then 14 billion years later, or actually even a much shorter time later, mostly what we find is matter. So the question is, what happened to the antimatter? Does that make sense?
Yeah, thank you.
More questions? It seems like there are no more questions, Amar. So
Okay,
can
great.
we meet tomorrow then?
Yeah, tomorrow for you, later tonight for me, but I'll see
Yeah.
you in lecture 2. Bye.
But I have a little bit rest of the daytime.
Bye.
Yeah, see you then.